Welcome to HVAC Engineering-Techie channel. This is the channel where we talk all things HVAC. We talk about engineering design, construction, equipment, systems, tab extensively, controls, and efficiency and system performance. So this video is intended to give you an education to advance your career. Today we're talking about altitude effect on HVAC. Now, I know we've already talked about this in some of the basic math and physics, but we're going to take it a little bit further so you get a little bit more depth on everything that altitude can affect in HVAC. But before we do that, I'd like to ask you a really big favor. Would you mind subscribing, become a subscriber by hitting the button down below that says subscribe and hitting the thumbs up, which is a like symbol? I would really appreciate it. It's not that it costs anything. It's absolutely free. We never cost you anything. And it's painless. I will never contact you about anything. It's those two things are used by Google to evaluate this video on their platform. So that would really help me. If you do that, I'd really appreciate it. You only need to do it once, by the way, but if you become a subscriber, it would really help me out. Thank you. Let's start talking about altitude effect on HVAC. Let's get started. All right, so let's talk physics to the altitude, air at altitude. So this basically is a chart of density of air at different temperatures and different altitudes. Now, the one thing about this chart is chart is basically up for dry air. It's calculated very specific for dry air conditions, not moist air. Now, the reason I say that is because if you take a site chart and you remember we talked about let's see if we can get the next line up here. Okay, specific volume. Specific volume is a reciprocal of density, so it's 1 over the density. And if you take your site chart and you look up 70-degree air at 50% humidity, you'll get 13.5. If you take this 70-degree air at sea level, it's 0.0749. Divided by 1, you get 3.35. That's the difference, because this is dry air. This is dry air, and the psych chart, psychometrics, right, it's all about moist air, so it's moisture difference. Now, in reality, though, it doesn't matter, because we're using this chart to calculate the difference. The conditions are different. So whether you use dry air or moist air, it doesn't matter, as long as you use dry air for both measurements or moist air for both measurements. Now, if you're doing a heat gain or something, it's important you have the moisture involved in there, but for altitude calculations, it really doesn't matter. You can if you want, but it's not necessary. So this table is dry air, like I talked about. To change dry air, to change these numbers to what it would be with moisture, multiply times this factor is 0.988973, and that'll get you the moisture contents if you want. Not sure it's necessary. You can just use the differences the way they are. So this particular two, I looked these two. One is 7,000 feet at 40 degrees. So here's 40 degrees at 7,000 feet. So this is looking at the outside airs. This 0.0613, and that would be 16.31 specific volume. So you can tell at altitude, it takes a whole bunch more cubic feet of air to move the same amount of pounds as you would at sea level. So at sea level, we're talking 13.35. At 7,000 feet, we're talking about 16.31. Big difference. And that's why we have to do these altitude calculations to make sure we have enough capacity to do what we're doing. So this was an 18.15% reduction in density, but it was a 22.17 increase in specific volume. So you can see for a smaller change in density, we needed a larger change in specific volume, because that's just the criteria of that. So the changes in altitude affects horsepower required for fans, affects the size of AC and heating units, affects temperature settings of capillary sensors and thermostats. And we'll get into that a little later. So remember that a fan is a constant volume device. A fan can deliver 1600 CFM at sea level, will still deliver 1600 CFM no matter what the altitude is. But the static pressure and horsepower requirements will change in that fan as it moves up. So here's an example. The catalog lists an AC unit supply fan delivering 1600 CFM at 1 1/4 inch static pressure at sea level with a 0.944 brake horsepower, what will be the CFM, static pressure, and brake horsepower if this fan is operated at 7,000 elevation? Now remember, the fan's a constant flow device, so it'll still have 7,000 CFM. That won't change, but other things will change. So the formula is static pressure 2 over static pressure 1 equals density 2 over density 1. And this stands for density. I know in water calculations it stands for pump diameter, but impeller diameter. For here, this is density. So you have static pressure 2 over 1.25 equals 0.0578, which is the density of air at 7,000 feet, times 0.0749, which is a sea level. And then the way I always do it is, you can do this as a straight ratio, but I always do cross multiplication, which is multiplying this side by this side, and then dividing out this side, and you get the answer. So that's 1.25 times 0.058 divided by static pressure over that, and that equals 0.915 static pressure at 7,000 feet. So you can see it was 1.25 inch, now it's down to 0.9. So the static pressure has dropped. So now brake horsepower 2 over brake horsepower 1 equals density 2 over density 1. And that equals 0.94 over that ratio. And that equals, if you cross multiply again, you get 0.68 brake horsepower. So was 0.94, so now it's 0.68. So you can see that the horsepower is going down and the static pressure went down to that fan. So now the second thing you have to talk about is how much does it derate a system capacity due to altitude. So we're going to talk about that now. This is a little bit different. A building at 6,000 foot elevation has a heat loss of 38,000 BTU for a heater. The heater with 1,200 CFM at a 30-degree delta T can provide 40,000 BTU at sea level. How much heat will this heater provide at 6,000 feet? So we need 38,000 feet. That's what the engineer's calculation said we need in heat. This heater will do 40,000, so that should be good. It's got more than required, but what will it have? It'll do this at sea level. What will it do at elevation? Formula again is specific heat times 60 divided by specific volume times CFM times delta T. The specific heat is 0.2404. At sea level, we get the 13.35 again, the 1 divided by 0.0749. 0.2404 times 60 divided by 13.35, which is that number, times CFM times the split, equals 38,896. So at sea level, that works good. We got that 38,000. Okay, at 6,000 foot air density, it goes to 0.0636, which means the specific volume is 15.72. So we work this equation again, the 0.2404 times 60 divided by 15.72 times 1,200 times 30 equals 33,032 BTU, which is, we don't make the 38,000 that we require to heat the space. So what's the size heater be required to provide 38,000? So if this one won't do it, what do we need? And so if we take that 15.72 over 13.35, gives us a ratio 1.178 to multiply that times 38,000. Well, we need a heater that'll do 44,000 BTU at sea level. So this one will do 40,000, so it's not a good enough heater. We need a bigger heater to get up to at least 44,000 at sea level. That will give us 38,000 at 7,000 feet. So now they also increase CFM to increase capacity due to altitude. So, if you have a package unit that can't be you can't just speed the air up, which on an air handler you can, you might have to have a bigger unit at altitude to do the job. This is looking at an air handler. So if we have an air handler produces 25,930 BTU with 1,200 CFM at the sea level with a 20% split, what CFM will be required for the same air handler to deliver 25,000 BTU at 6,000 feet? Get my cursor in the right place here. So again, BTU times sensible heat times 60 over specific volume times CFM times delta T. Specific heat's that. So air at the density at sea level is 13.35. So we know that this system is going to do 25,930 at sea level. At 6,000 feet, the specific volume goes to 1572. So if we take the 25,930, which is the sea level, divided by 2404 times 60 divided by 1572 times 20 equals 1413. So we got 1,413 CFM. So we're going to have to, if this was an air handler, we would have to increase the CFM to that level to be able to move the right amount of heat. And then we have to make sure the coil in this unit is capable of handling 1,413 CFM at a reasonable pressure loss that the system doesn't falter to do that. If it's a package unit, we're going to have to go from a 3-ton up to 3.5 ton to get the right amount of air. So that's how we're going to have to change that to get there. Now you could also use a straight ratio on this. Just the ratio is 1.177528. Multiply it times 1,200, it comes up to 1413. So that's probably easier to do it that way. But either way, we know we have to have more air because we have to have more pounds of air to get the pounds of air up to what it would do at sea level so we can transfer the same amount of heat. And of course, this works for cooling and heating the same. So these are altitude what we have to do to be able to tell where we're going with that. Okay, so now let's talk about capillary sensors. Remember, capillary sensors have refrigerant in them. It's a closed system. This is actually a tube, and there's refrigerant inside of there. And as the temperature changes, the refrigerant expands and contracts. And as it expands and contracts, it pushes on a bellows that's hooked to a switch. So this is a one at sea level. So we got 14.5 psi, somewhere around 15 psi in the, I don't know exactly what pressure it is, but somewhere around in there. And as it gets colder, this pressure, the pressure in it drops, and it allows the barometric pressure to push down and trip the switch. And so these are designed to trip at 35 degrees. So they want them tripping right above freezing, so we protect the coil from freezing on a unit. And so this is what it would work at sea level. But if you have that same thermostat at elevation at 7,000 feet, so this would be 11.4 psi. So we have much less barometric pressure. So, but this doesn't change inside of here. So this is actually bowed this pressure plate up, making that sensor further away from the point. So as it gets cold, so it doesn't actually switch, and this actually trips at 43 degrees. So you have to adjust this down so that it will now trip at 35 and not 43. So you trip at 43, you get lot of false turnoffs, which is really irritating to operations. So this has a 23% offset due to the elevation. So the other way you can do this is not use capillaries. Use a averaging thermistor sensor, which has just a big long wire with a whole bunch of thermistors in it that they read the resistance in series, and from that they know what the total temperature is. So capillaries also have somewhat of a problem with them, and it's how they're installed. Whereas a thermistor, you can install it any way you want to. It doesn't really matter, just as long as you kind of get it around the coil area to get an average. The whole idea of these sensors is to get an average and not let one little space dictate it. So the directions from the manufacturer state that this capillary needs to go through every square foot of a coil. And normally we just go through the middle of a square footage. And the specification is it be horizontal, down, horizontal back, down, horizontal back. So it's a serpentine type thing across the coil. And it's actually very, very important for a capillary that you do it that way. And the reason is because the refrigerant here can become liquid. And if I've seen it done all kinds of ways wrong. If you just kind of zigzag across the coil, these low points will gain liquid refrigerant. And now it doesn't have the same accuracy as it does when it's done horizontally and it's all vapor in there. So how you install these is very, very important. The thermistor doesn't matter, right? It can be installed anyway. So anyway, check your freeze stats and check your averaging sensors. If they're capillaries and air handler, need to be calibrated properly. And this adjustment will need to be adjusted to be proper. Altitude effects, fan horsepower, CFM for equal capacity, coil selection for capacity, and any capillary control device. This is what altitude affects, and that's what the things we need to check against for altitude. Well, this is a real short lesson. I hope that was beneficial. Again, I'd appreciate it if you become a subscriber or give me a thumbs up. Hope you have a great day, and catch you on the next one.